Hey folks, welcome to our introduction to electric current. And we're going to start off right away with an equation. So the definition of electric current. So electric current, the symbol we use for electric current is an I. I don't know why we use an I, but we use an I. So this is electric current. Well, the definition of electric current is dq dt. In other words, it's simply current is a rate at which charge passes by. Okay, charge is measured in coulombs and time is measured in seconds. So current could be measured in coulombs per second, but we have a name for that. We call it an amp or an ampere. It's named after ampere, or just simply capital A. So example, let's say you have a 60-watt incandescent light bulb in your house and a lamp. That light bulb will draw half an amp of current. That means 0.5 coulombs of current or of charge goes through that light bulb every second. Now, if you recall, one electron or proton is equal to 1.6 times 10 to the negative 19th coulombs. So if you calculate what half a coulomb is, you're talking about a large number of electrons that pass through that light bulb every second. Or put another way, a lightning bolt is about 20 coulombs of charge. So a 60-watt bulb in your house basically has one lightning bolt pass through it every 20 seconds. I'm sorry, every 40 seconds. So when current flows, we're talking about a lot of charge. Why don't we notice it, or why don't we see lightning bolts over our house and everything? Well, that's because what's happening is, let's say here's a wire. A wire is a lattice of positive charge, and then there's negative charges. And the negatives are moving, okay, but they're always nearby, they're positives. There's no net charge in that light bulb, thankfully. So the overall charge in the light bulb is always neutral, but we have a flow of electrons near their positive partners. Now, why does charge flow? Okay, so let's say you have a very simple circuit. Let's say you have a light bulb, for instance, and a flashlight. Okay, so if you have a light bulb, if you were to look at a light bulb really carefully, okay, so there's the glass on top, you would see two parts that conduct on the outside. There's a little metal part down here, like so, and then the actual screw-in socket has metal on it. And if you were to peer into there very closely, here's what you would see. You would see a filament, okay? And that filament would be attached to the bottom and then to the side, like I've drawn there, okay? So a filament is basically made of a specific metal. Most filaments in incandescent bulbs are made of tungsten. And the idea is when electrons pass through the tungsten, it heats the tungsten up, and then the tungsten glows. Well, how do you make the electrons flow through that tungsten filament? Well, in a flashlight, you'd hook it up to a battery. So let's say here's your battery, okay? Now, battery has a positive and a negative end, okay? And the idea is you would hook one wire up to the negative end to one part of this, and you would hook the positive end up to the other conductor of a light bulb. So if you were to tear apart a flashlight, that's basically what you're going to see. And what happens is electrons, okay, flow through the circuit, like so. And they're going to flow this way, okay? And that is called real current. Okay, so what actually happens in a real-life circuit is electrons flow. Now, a couple notes. What is the net charge in the battery? It's 0. Okay, so where are these electrons coming from? Well, these electrons are already in the wires, the bulb, the battery. Okay, they're part of the overall neutral object. Everything in this picture is neutral. All the battery does is push the charge. It's kind of like putting a pump into a well. The pump itself doesn't have any water, but when you put it into a well, it'll push that water for you. Well, think of a battery as the same thing. When you put the battery into a conductor, that battery will push charge for you, okay? Now, a simpler version of this is the same thing, but a simpler version is, let's say here's your filament. So we're just going to make it real simple picture. It's a cylinder now, okay? And let's say here's your battery, okay, with the plus and the minus side, and you've hooked it up like so, okay? So what ends up happening here is the battery sets up an electric field in that tungsten filament, okay? And that electric field goes from the positive end of the battery to the negative end of the battery. So that would be your electric field pointing left, okay? So, it would kind of point this way. That'd be your electric field. Now, you might recall from earlier chapter, if you have an electron in there, electron will feel a force that's in the opposite direction of the field, so the electron will flow to the right in that filament, okay? Now, again, that's called real current. What really happens is electrons flow. Positive charges aren't allowed to flow because they're stuck in the nucleus. They're protons, okay? So what a battery does is it sets up a permanent electric field. Up until now, in our first part of the semester, we talked about charges moving around until the electric field is zero. Well, now the battery prevents that from happening. The battery keeps a voltage. It keeps the electric field constant in there, okay? Now, this is what really happens. Electrons flow. But if you talk to an electrician, if you talk to even electrical engineer, and even in some cases, if you talk to a computer scientist, okay, even though they all know that electrons flow, that's not how they think of it. Okay? So we have two different kinds of current we talk about. We talk about real current, and then we talk about something called conventional current. Okay, so conventional current. What's the difference? Okay, well, real current's what we've been describing. Okay, so for instance, imagine that I have two buckets. Okay, so I got two buckets here, and they're neutral, which means they have an equal amount of plus and minus charge. So here are my two buckets. Okay, and let's say I hook a battery up like so to the two buckets. Okay, well, what that battery will do is it'll suck electrons out of the right-hand bucket and deposit them into the left-hand bucket. So what will end up happening is the left-hand bucket will end up with a negative charge and the right-hand bucket will end up with a positive charge. Okay. Well, that's what really happens. But if you talk to an electrical engineer or electrician, here's the way they think of it. Okay. And so we'll say have the same two buckets, same initial neutral charge like so. Okay. And same battery. All right, so you hook up the same battery like so. All right, just like that. Well, here's what electricians and electric engineers and so on think of. Okay, they think of positive charge flowing this way through the battery. Okay, now we know that positives don't move, but that's how they think of it. Okay, so here's what ends up happening. Now, if you still look at the situation, the right-hand bucket still ends up with a positive charge, and the left-hand bucket still ends up with a negative charge. So it turns out that it doesn't matter which way we think of this. So in a lot of the problems that we're going to do, especially in our next chapter, we're going to actually deal with conventional current, even though we know it's not what really happens. We're going to use that because, well, if you go into electrical engineering or if you become an electrician or even if you do computer science, you're going to often think of it as positives moving. Now, why on earth do we do that? All right. Well, it's kind of a complicated question, but the short answer is way long ago, Ben Franklin messed up. All right. And when I say messed up, not really. The man was a genius, but he did have one thing kind of wrong when he was thinking about electricity. As Ben was thinking about electricity, he was thinking of it as a fluid, which is actually pretty much correct. And what he said was if an object has too much fluid, he called that positive. And if an object has too little fluid, he called that negative. And that's where we get our convention for positive and negative. Well, what Ben didn't know is that charges come from atoms, and the part of the charges that move are the negative charges, the electrons on the outside of the atom. Well, if you think about it, if an object has too many of this fluid, which we're talking about electrons, well, really it's negatively charged. And if the object has too little of this fluid, which is really electrons, then the object's positively charged. So Ben kind of had it backward. Because of that, we have used his convention ever since. So we use the wrong convention and we stick with it. And I don't know, I guess we're stubborn. Okay, so that's an introduction to electric current. Also, I'll mention one more thing. Current's often measured in amps, but if like for a light bulb in a flashlight battery, let's say, we're often going to talk about milliamps. We're talking about 10 to the negative third amps, small fractions of an amp. And you will even have currents that are in the microamp range. So for instance, if you get shocked, it's probably in the microamp range. All right, so in the next video, we'll talk a little bit of chemistry with you. So I hope you enjoyed this video and have a good one.